What if I told you that the universe holds secrets so baffling, even our brightest minds can only guess at the answers? Picture this, a force so powerful it bends space itself, yet invisible to our eyes, dark energy, stretching the cosmos apart at an accelerating rate. Or consider the eerie silence from countless planets that should, statistically, be teeming with life. Where is everyone? These aren't just science fiction plot twists, they're real, unresolved puzzles that keep astronomers awake at night. And they're just the beginning. For centuries, humans have gazed at the stars, weaving tales to explain the unknown. But today, armed with cutting-edge technology and centuries of accumulated knowledge, we're closer than ever to unraveling these cosmic enigmas, or at least proposing theories wild enough to match them. From the mind-bending idea that our universe is a hologram to the haunting possibility that we're alone in an unimaginably vast expanse, the mysteries of space challenge everything we think we know. And that's exactly what makes them so thrilling. In this journey, we'll dive into 30 of the most compelling theories crafted to explain space's biggest head-scratchers. Some sound like they're ripped from the pages of a fantasy novel, black holes as gateways to other dimensions, or ancient alien megastructures lurking in distant star systems. Others are grounded in razor-sharp math but still feel like they defy logic. But here's the real kicker. Each of these ideas, no matter how outlandish, is backed by real science and real scientists willing to stake their reputations on them. So buckle up. By the time we're done, you might just see the cosmos and our place in it in a whole new light. Imagine walking through a room filled with invisible furniture. You can't see it, but every time you bump into something solid, you know it's there. That's exactly how scientists approach the mystery of dark matter. We can't see it, touch it, or even detect it with traditional instruments, yet its gravitational pull shapes galaxies, bends light, and holds the universe together. In fact, if you added up all the stars, planets, and cosmic dust we can observe, it would account for less than 20% of the universe's total mass. The rest, that's dark matter's domain. So what is this ghostly substance? One leading theory points to WIMP, weakly interacting massive particles. These hypothetical particles are thought to pass through ordinary matter like shadows through a wall, barely leaving a trace. Then there are actions, ultralight particles so elusive they could be streaming through you right now without a flicker of interaction. The catch: after decades of hunting with underground detectors, particle colliders, and space telescopes, we've yet to catch one red-handed. Here's where it gets even stranger. Dark matter doesn't just evade detection, it defies the rules. Unlike normal matter, it doesn't absorb, reflect, or emit light. It doesn't clump into planets or stars. Instead, it forms vast, invisible scaffolds around galaxies, a cosmic skeleton we only notice when galaxies spin way faster than they should, or when light warps around what appears to be empty space. Some researchers wonder if we're missing something fundamental. Maybe dark matter isn't a particle at all, but a flaw in our understanding of gravity itself. Others propose entire hidden dimensions where these particles could be hiding. But until we crack this puzzle, one thing's certain: the universe is far weirder and far more mysterious than we ever imagined. The cosmos teems with countless stars, each potentially hosting planets in the sweet spot for life. So where are all the aliens? This glaring contradiction is the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "But where is everybody?" Statistically, the universe should be buzzing with activity. With hundreds of billions of galaxies, each filled with even more stars, the numbers suggest civilizations ought to be common. Yet our telescopes pick up nothing but silence, no signals, no megastructures, no visitors. It's as if the universe is a stage set for a play where all the actors have vanished. One chilling explanation is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar levels. Think of it as a cosmic obstacle course, where most civilizations wipe themselves out before they can colonize the stars. The filter could lie in our past, meaning we're miraculously rare survivors of some near-impossible step, like the leap from single-celled to complex life. Or worse, it might wait in our future nuclear war, climate collapse, or runaway AI could be the traps that snuff out intelligence before it spreads. If that's the case, humanity's window to reach beyond Earth might be frighteningly narrow. Then there's the zoo hypothesis, the idea that advanced civilizations are out there, but they're deliberately avoiding us, treating Earth like a protected wildlife reserve. Perhaps they're observing under strict non-interference rules, or maybe we're just too primitive to be worth contacting. It's a humbling thought, like ants unaware of the humans stepping carefully around their hill. Others argue that spacefaring civilizations inevitably self-destruct. Imagine a species mastering fusion power but failing to control its own greed or aggression. Or picture a culture so addicted to virtual realities that it loses interest in the physical universe. The truth might be bleak. The universe could be littered with the ruins of civilizations that burn too bright too fast. But here's a twist. What if we're simply early? The universe is 13.8 billion years old, but it's got trillions more ahead. Intelligent life might just be rare for now, with humanity among the first sparks in a dark, young cosmos. If that's true, the real era of galactic civilization and the solutions to Fermi's question might lie far in the future. Until then, the silence isn't a warning, it's an invitation. The stars are waiting, and the mystery is ours to solve. Black holes aren't just cosmic vacuum cleaners, they're also the universe's most baffling puzzles. In the 1970s, Stephen Hawking made a discovery that turned physics upside down. Black holes leak. They slowly radiate energy, now called Hawking radiation, and over unimaginable eons they evaporate entirely. But here's the catch. If a black hole vanishes, what happens to all the information it swallowed? According to quantum mechanics, information can't be destroyed. Every particle, every atom that falls in should leave some kind of fingerprint, even if it's scrambled beyond recognition. Yet Hawking's math suggested black holes erase it forever, shredding the universe's ledger. This clash between quantum theory and gravity became the black hole information paradox, and it's haunted scientists for decades. One radical solution comes from the holographic principle, the idea that all the information inside a black hole isn't lost, it's smeared across its event horizon like a cosmic etch-a-sketch. Picture this: a three-dimensional star collapsing into a black hole gets encoded as a two-dimensional pattern on the surface, a holographic projection of its former self. It's as if the universe keeps a backup copy, ensuring nothing truly disappears. This theory bends our understanding of reality, suggesting that space itself might be a hologram, with the true nature of existence playing out on some distant, unseen boundary. Then there's the firewall hypothesis, which cranks the weirdness up further. Imagine falling toward a black hole's event horizon, expecting to pass smoothly into oblivion, only to hit a searing wall of energy that vaporizes you instantly. According to this idea, the paradox forces a brutal trade-off. Either information gets preserved, but at the cost of relativity's smooth spacetime, or relativity wins and quantum mechanics breaks. It's like the universe has to choose between frying you or erasing your existence from history. But perhaps the boldest twist comes from recent work on quantum entanglement, suggesting black holes aren't destroyers but cosmic alchemists. Information might escape not through radiation but via invisible threads linking particles inside and outside the black hole, a quantum teleportation that preserves the universe's rules. Every solution feels like science fiction, yet each is grounded in cutting-edge math. And that's the beauty of this paradox. It's not just about black holes. Crack it, and we might finally uncover the hidden glue that stitches reality together. If the universe were a loaf of raisin bread baking in the oven, you'd expect the raisin's galaxies to slowly spread apart as the dough expands. But here's the twist, that bread isn't just rising, it's accelerating as if some unseen hand cranked up the heat. That's the enigma of dark energy, the mysterious force pushing the cosmos apart faster and faster. When astronomers first spotted this in the late 1990s by observing distant supernova, it upended everything we thought we knew about cosmic fate. Gravity should be slowing the expansion, not losing the tug of war. So what's behind this runaway effect? Einstein might have accidentally predicted it a century ago with his cosmological constant, a mathematical fudge factor he inserted into his equations to keep the universe static. He later called it his biggest blunder when Edwin Hubble proved the universe was expanding. But today, that same constant is the leading explanation for dark energy, an inherent property of space itself, where empty vacuum somehow generates repulsive gravity. Think of space as a stretchy fabric with built-in springs. The more it expands, the more it pushes. The problem, when we calculate how strong this effect should be, quantum physics gives a number 10 to the power of 120 times too large. That's like predicting a light breeze but getting a hurricane capable of shredding spacetime. Then there's quintessence, a dynamic cousin of the cosmological constant. Named after the ancient fifth element, this theory suggests dark energy isn't constant at all but a fluid-like field permeating space, its strength ebbing and flowing over time. Picture blowing up a balloon with patches of weaker rubber. Some areas expand faster, others slower. If true, this could mean dark energy's push might one day weaken or catastrophically intensify, ripping apart galaxies, stars, and even atoms in a Big Rip scenario. The wild card, modified gravity theories that ditch dark energy entirely, proposing Einstein's equations break down on cosmic scales. Imagine if the force holding you to Earth subtly changed its rules across light years, like discovering traffic laws differ mysteriously once you cross state lines. But every alternative so far creates new problems while failing to explain all the observations. Here's what truly boggles the mind. Dark energy makes up 68% of the universe's energy budget, yet we have no idea what it physically is. It doesn't clump, interact with light, or leave any trace except its gravitational fingerprint. Some speculate it's tied to extra dimensions or bubbling quantum foam. Others wonder if we're seeing shadows of a sibling universe bleeding into ours. One thing's certain, solving this mystery won't just rewrite cosmology textbooks, it could reveal whether the cosmos ends in ice, fire, or something beyond our wildest imagination. We all know the story. Nearly 14 billion years ago, an infinitely dense point erupted, birthing space, time, and everything we see today. But here's the question no one can definitively answer: what lit the fuse? The Big Bang describes the universe's explosive growth, not its origin. It's like walking into a movie 20 minutes late. You see the action, but the opening scene remains a mystery. One compelling lead is cosmic inflation, the idea that a fraction of a second after the bang, the universe underwent a growth spurt so violent it stretched space faster than light itself. Picture blowing up a balloon so rapidly that tiny quantum wrinkles on its surface became the seeds for galaxies. Inflation solves cosmic puzzles, like why the universe looks eerily uniform in all directions. But it raises another. What sparked that? Some theorists propose a bizarre quantum fluke, a false vacuum where space held pent-up energy until it catastrophically decayed, unleashing inflation like a cosmic matchstick. Then there's the cyclic model, where the Big Bang wasn't a beginning but a rebound. Imagine two parallel universes colliding in higher dimensional space, their impact fueling our cosmic dawn. Or picture a universe that expands, crunches back, and bounces anew in an endless cycle. These ideas dodge the something from nothing dilemma by suggesting time didn't start at the bang, it reset. But the wildest guess, the multiverse. If inflation is eternal, as some models suggest, our universe might be one bubble in a frothing sea of others, each with its own laws. The bang, then, wasn't a singular event. It was just our local bubble inflating. String theory takes this further, proposing universes could arise from higher dimensional brains clashing like symbols in a hidden dimension. The catch: observing these theories is like trying to reconstruct a fireworks blueprint from its ashes. Light from the bang's first moments is lost to time, and any traces of pre-bang physics might be forever scrambled. Even gravitational waves from inflation, if they exist, are whispers drowned out by cosmic noise. We're left with math and imagination tools powerful enough to sketch possibilities, but not yet to confirm them. That's the thrill of this mystery. The answer might rewrite not just cosmology, but our very definition of reality. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1970s, scientists expected their trajectories to be predictable, governed by the familiar tug of gravity from the Sun and planets. But something odd happened. As these twin probes hurtled toward the edge of the solar system, they began slowing down slightly more than calculations predicted, as if an invisible hand was gently tapping the brakes. This tiny deviation, just a fraction of a nanometer per second squared, became known as the Pioneer anomaly, a puzzle that lingered for decades. At first, researchers suspected mundane explanations like fuel leaks or instrument errors. Then came the thermal theory. Heat radiating unevenly from the spacecraft's nuclear power sources could have acted like a faint rocket thrust in reverse. Picture a car idling with one side slightly warmer than the other over time. That imbalance might nudge it off course. Meticulous computer models seemed to confirm this, but skeptics noted discrepancies. If thermal pressure was the culprit, why didn't other spacecraft like Voyager show the same slowdown? This inconsistency sparked wilder theories. Some proposed modifications to Newton's laws of gravity, suggesting that on cosmic scales, gravity behaves differently than we've assumed. Imagine if the rules of baseball subtly changed once players left the stadium. What works on Earth might not apply in deep space. One such idea, modified Newtonian dynamics (MOND), tweaks gravity's equations to explain galactic rotations without invoking dark matter. Could the Pioneer anomaly be a sign that MOND's adjustments also affect spacecraft? The math tantalized, but when tested against other probes, the evidence crumbled. Then there's the quantum vacuum hypothesis, the idea that empty space isn't truly empty, but a seething foam of virtual particles. If these particles exerted minuscule drag on the Pioneers, like a swimmer fighting an invisible current, it might account for the anomaly. But here's the catch: quantum effects are typically too weak to influence something as massive as a spacecraft. Unless, of course, we're missing a key piece of quantum gravity, the holy grail of physics. The Pioneer anomaly's resolution came with a mix of relief and disappointment. Detailed analyses in 2012 traced most of the deceleration back to heat recoil after all, though tiny quirks remained. Yet the legacy of this cosmic whodunit endures. It reminds us that even in the era of precision astronomy, the universe can still throw curveballs, and that the most subtle anomalies often lead to the boldest breakthroughs. Who knows what other secrets might be hiding in the quiet drift of a spacecraft's path? On an ordinary August night in 1977, a quiet radio telescope in Ohio picked up something extraordinary. A 72-second burst of radio waves so powerful, so perfectly tuned to the frequency hydrogen emits, that astronomer Jerry Rood wrote, "Wow." In red ink next to the data, that scribble became legendary. The wow signal remains the closest we've ever come to hearing what might be an alien hello, a fleeting whisper from the cosmos that vanished as mysteriously as it appeared. At first glance, the signal checked all the boxes for an artificial transmission. It blasted 30 times louder than cosmic background noise, exactly at 1420 MHz, a frequency shielded from natural interference, almost as if someone chose it deliberately. It matched predictions for how an intelligent civilization might broadcast its presence, like a lighthouse beam sweeping past Earth. But despite decades of searching that same patch of sky, the signal never repeated. Not once. So what was it? One camp argues for cosmic coincidence. Hydrogen is the universe's most abundant element, and the WOW signal's frequency aligns with its emission line like catching a random shout on a crowded street tuned precisely to your name. Maybe it was a bizarre amplification of natural radio waves, bent by a passing comet or reflected off interstellar plasma like sunlight glinting off a distant window. In 2017, researchers suggested Comet 266P/Christensen, which happened to be crossing that region of space at the time, could have been the culprit. But critics point out comets don't emit strong radio waves at that frequency, and the signal's narrowband purity still feels engineered. Then there's the tantalizing possibility it was artificial, just not alien. Cold War-era satellites or secret military experiments could have leaked a transmission, though declassified records show no matches. Even more intriguing, the signal's duration. 72 seconds is exactly how long the telescope's fixed receiver would have recorded a passing blip as Earth rotated. If the source was stationary, say a distant beacon, it would have lasted longer. That suggests the signal moved out of the telescope's field of view, like a ship turning its spotlight away. The darkest twist, it might have been a one-time event we missed by cosmic seconds. Imagine an alien transmitter sweeping the galaxy in a narrow beam, briefly painting Earth with its signal before moving on. If their rotation period didn't sync with our listening schedules, we'd never catch it again. Or worse, what if it was a deliberate message and we failed to reply in time? 47 years later, the WOW signal endures as both inspiration and cautionary tale. It's a reminder that the universe might be shouting, but we're still learning how to listen. And until another signal comes, if it ever does, that lonely WOW on a faded printout remains our most tantalizing cosmic maybe. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations. A visitor from interstellar space, tumbling end over end at nearly 200,000 miles per hour. Named Oumuamua, Hawaiian for Scout, this object wasn't just the first of its kind ever detected. It was weird. For starters, its shape, somewhere between a cigar and a pancake, bore no resemblance to any known asteroid or comet. Then came the real kicker. As it slingshotted past the sun, Oumuamua sped up, not from gravity, but as if pushed by some unseen force. Most comets accelerate when sunlight vaporizes their ices, creating a visible tail of gas and dust. But Oumuamua showed no coma, no tail, no outgassing at all, just pure, unexplained motion. The first theory proposed it was a hydrogen iceberg, a chunk of frozen gas evaporating invisibly in sunlight. Yet hydrogen ice is so fragile, it shouldn't survive an interstellar journey. Then came the nitrogen iceberg idea, a splinter from a Pluto-like world, nitrogen slowly boiling off like dry ice in sunlight. Problem: no known process creates such pure nitrogen chunks in space. Enter the most controversial explanation: artificial origin. Harvard astronomer Avi Loeb famously suggested Oumuamua could be a light sail, an alien probe propelled by starlight. Its flat shape, unnatural acceleration, and trajectory conveniently passing close to Earth all fit. Critics rolled their eyes, pointing out that extraordinary claims require extraordinary evidence. But Loeb countered, shouldn't we at least check? After all, dismissing the possibility outright risks the very bias that kept scientists from believing in meteorites for centuries. Here's where it gets thornier. By the time we noticed Oumuamua, it was already racing away, too distant for detailed observations. Was its weirdness just a trick of limited data? Or did we miss our only chance to study an interstellar artifact up close? The debate rages because Oumuamua represents something bigger, a cosmic Rorschach test. To some, it's a quirky space rock revealing gaps in our comet theories. To others, it's proof we're not alone. and that the universe might be sending scouts we're too blinkered to recognize. Either way, its legacy is clear. The next time an interstellar visitor drops by, we'll be watching like hawks. Somewhere beyond the Milky Way's glittering disk, hidden in a region astronomers call the Zone of Avoidance, lies a gravitational mystery powerful enough to yank entire galaxies off course. Imagine tossing a handful of marbles onto a stretched bed sheet only to watch them all roll toward some unseen weight in the darkness. That's the Great Attractor in action, a cosmic anomaly dragging thousands of galaxies, including our own, toward it at over 14 million miles per hour. The first clues emerged in the 1970s when astronomers noticed something odd. Galaxies in our local supercluster weren't just drifting apart with the universe's expansion. They were also streaming toward a single point, like leaves caught in a hidden current. But when they tried to pinpoint the source, they hit a wall, literally. The Milky Way's dense plain of gas, dust, and stars blocks our view in that direction, creating a blind spot spanning 20% of the sky. It's like trying to spot a lighthouse through a thunderstorm. Early theories suggested a supermassive cluster of galaxies might be the culprit, something with the mass of tens of thousands of Milky Ways, and in part they were right. The Norma Cluster, a dense knot of galaxies about 250 million light-years away, does contribute to the pull. But here's the hitch: when astronomers tallied up its gravity, it explained only part of the attraction. The rest still missing. That's where things get speculative. Some propose an even larger structure lurking behind the Zone of Avoidance, perhaps a supercluster so vast it rewrites our cosmic maps. Others wonder if dark matter, already the universe's invisible scaffolding, has clumped into an unimaginably dense knot, warping space-time like a hidden whirlpool. There's even a fringe idea that the Great Attractor isn't a single object at all, but the fingerprint of a higher dimensional ripple bleeding into our universe. The most tantalizing clue came in the 2010s when astronomers peered past the Great Attractor using infrared and radio telescopes, piercing the Milky Way's veil. What they found was jaw-dropping: an even larger gravitational sinkhole, the Shapley supercluster, 8 times more massive than the Great Attractor and 650 million light-years distant. It's like discovering the river you've been floating down empties into an ocean. Together, these titans might solve the puzzle, but the math still doesn't quite add up. Perhaps the real lesson here is how little we see of the cosmic web. The Great Attractor reminds us that even with our most advanced tools, we're still mapping the universe with a flickering candle. Every time we push the boundaries, we find deeper currents, vaster structures, and new mysteries tugging at the edges of our understanding. Look up at the moon, that familiar, cratered face that's lit our nights for billions of years, and you might never guess it was born from cosmic violence. The leading theory of its origin reads like a blockbuster disaster movie. Roughly 4.5 billion years ago, when the solar system was still a chaotic construction zone, a Mars-sized protoplanet named Theia smashed into young Earth with apocalyptic force. The impact was so colossal it vaporized rock, melted entire continents of crust, and hurled enough debris into orbit to form a glowing ring of molten shrapnel around our planet. Over time, that debris coalesced into the moon we know today. This is the giant impact hypothesis, and it elegantly explains so much: why the moon is surprisingly large compared to Earth, why it lacks a dense iron core like ours, Theia's core, merged with Earth's, and why lunar rocks share eerie geochemical similarities with Earth's mantle. But scratch the surface and the plot thickens. If Theia was a foreign body, why do oxygen isotopes in lunar samples match Earth so precisely? It's like finding 2 identical snowflakes in a blizzard, possible, but statistically unlikely. Some theorists argue Theia might have formed in the same orbital neighborhood as Earth, sharing its isotopic recipe. Others propose the impact was so violent it thoroughly mixed both worlds' materials before the moon formed. Then there's the angular momentum problem. The collision should have sent Earth spinning much faster than it does today. Where did that extra spin go? Maybe it was transferred to the Moon's orbit by gravitational tides, but the math remains fuzzy. This uncertainty has kept alternative theories alive. The co-formation theory suggests the Moon and Earth condensed together from the same primordial cloud, like siblings born from the same cosmic womb. It explains their chemical kinship but falters on the Moon's lack of iron. Without a giant impact, why wouldn't it have a core proportional to Earth? Then there's the capture theory. The Moon might have been a rogue body snagged by Earth's gravity. It's a poetic idea, a celestial drifter adopted by our planet, but orbital mechanics make it improbable. For capture to work, the Moon would have needed to shed enormous energy to slow down, like a speeding bullet somehow caught in a net without tearing through. The latest twist, a hybrid scenario where multiple impacts, not just one, built the Moon piece by piece. Picture a series of smaller collisions, each adding debris to a growing orbital disk. It's messier, but it might resolve the isotopic puzzle while accounting for the Moon's odd bulk. Or perhaps Theia's impact was even more extreme than we thought, a hit-and-run collision where the intruder grazed Earth, then escaped, leaving chaos in its wake. What's clear is this: the Moon isn't just a dead rock. It's a time capsule holding clues to Earth's violent infancy, and every new lunar sample, every computer simulation, brings us closer to unraveling the mystery. Until then, that glowing orb in our sky remains a reminder our planet's history was written in celestial fire. In the early morning of June 30th, 1908, a fireball brighter than the sun streaked across the skies of Siberia. Moments later, a blast roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima flattened 800 square miles of remote forest near the Tunguska River. Trees were felled like matchsticks in a perfect radial pattern, their trunks pointing outward from ground zero as if some giant hand had slammed down from the heavens. Windows shattered 600 miles away. Seismic stations across Europe recorded what looked like an earthquake, and yet no crater, no fragments, no obvious culprit. More than a century later, the Tunguska event remains the largest recorded impact event in human history, and we still don't fully understand what caused it. The leading explanation points to a stony meteoroid, roughly 60 meters wide, exploding in Earth's atmosphere 5 to 10 kilometers above the surface. Picture a cosmic boulder screaming through the air at 54,000 miles per hour, superheated air pressure building beneath it until boom, it detonates like a thermonuclear blast without ever touching the ground. This airburst theory fits the shockwave patterns and explains the absence of a crater, but there's a catch. Despite multiple expeditions, no significant meteoritic debris has ever been found. Not a single fragment larger than a grain of sand. Some researchers argue the explosion vaporized the asteroid completely, while others scour the peat bogs for microscopic diamonds or exotic minerals that might hold clues. Then there's the comet hypothesis. Unlike rocky asteroids, comets are icy conglomerates of dust and frozen gases. If a fragment of comet Encke, which happened to be passing near Earth that week, veered into our atmosphere, its volatile ices could have disintegrated explosively, leaving little residue. But again, the evidence is circumstantial. Without chemical traces in the soil or ice cores from that year, we're left with a compelling what if rather than proof. Now for the wildcard theories. Could Tunguska have been caused by a miniature black hole? In 1973, physicists proposed that a primordial black hole, no larger than an atom but as massive as a mountain, might have punched through Earth like a bullet through tissue, exiting somewhere in the North Atlantic. The entrance would have released a devastating shockwave without leaving a traditional impact scar. It's a fascinating idea, but here's the problem. Such an event should have produced a second explosion when the black hole exited, and no seismic records or ship logs from that era mention anything unusual. Even more speculative is the antimatter hypothesis, the notion that a chunk of antimatter from deep space annihilated upon contact with our atmosphere, converting entirely to energy in a flash of gamma rays. While this neatly explains the lack of debris, antimatter concentrations in space are vanishingly rare, making such an encounter astronomically unlikely. So why does Tunguska still captivate scientists? Because it's a warning. If a similar event happened today over a major city, millions could perish. In 2013, the Chelyabinsk meteor, just 20 meters wide, injured 1,500 people when it exploded over Russia. Tunguska was nearly 10 times more powerful, yet for all our advances in asteroid tracking, the solar system still holds countless objects too small to detect until they're alarmingly close. The Tunguska event isn't just a historical curiosity, it's a cosmic reminder that sometimes the universe throws curveballs and we may only get one chance to duck. Some stars flicker predictably like cosmic metronomes ticking away the ages, but then there's KIC 8,462,852, better known as Tabby's star, a celestial oddity that dims so erratically, so dramatically, it makes even seasoned astronomers scratch their heads. Located 1,500 light-years away in the constellation Cygnus, this star first grabbed attention in 2015 when citizen scientists flagged its bizarre light patterns in Kepler Space Telescope data. Unlike typical stars, which dip slightly when planets transit, Tabby's star plunged by up to 22% in brightness, like someone turning a dimmer switch on and off at random. And the dips weren't periodic. They came in clumps, sometimes lasting days, other times vanishing for years. The initial explanation leaned toward a colossal swarm of comets, thousands of them, maybe even millions, orbiting in tight formation. Picture a vast, dusty entourage blotting out the star's light as they pass. But there's a problem. Comets leave heat signatures, and follow-up infrared observations found no excess warmth. If it was dust, where was the heat? Then came the really wild idea. What if we're seeing a Dyson sphere, or at least pieces of one? The concept, dreamed up by physicist Freeman Dyson in the 1960s, imagines an advanced civilization constructing a massive energy-harvesting structure around its star. Maybe Tabby's star hosts aliens building megastructures, their half-finished project casting shadows across the cosmos. But before we jump to extraterrestrial conclusions, let's consider Occam's razor. Recent studies suggest a less sensational but equally fascinating culprit, a broken-up planet or moon. Imagine a world torn apart by gravitational forces, its debris field now drifting in a lopsided orbit, creating irregular eclipses. Observations in 2021 revealed the star's dimming is wavelength-dependent, meaning some colors of light get blocked more than others. That's a smoking gun for fine dust, the kind you'd expect from grinding planetary collisions. Yet the mystery isn't entirely solved. Why does Tabby's star also show a long-term fading trend, losing 3% of its brightness over a century? Dust from a single cataclysm shouldn't linger that long. Some theorize the star itself is unstable, coughing up enormous clouds of sooty material as it ages. Others wonder if we're witnessing a rare phase of stellar evolution, something no one's catalogued before. Here's what makes Tabby's star so thrilling. It's a reminder that the universe still holds phenomena we can't yet categorize. Whether it's shattered worlds, cosmic dust storms, or just maybe the fingerprints of intelligence, this star challenges us to keep looking up with open minds. After all, the most exciting discoveries often begin with a simple question: what on Earth or beyond could be causing that? Imagine a map of the universe so precise, it captures faint whispers from the dawn of time, the cosmic microwave background, or CMB. This afterglow of the Big Bang should be uniform, a static-laced tapestry of tiny temperature variations revealing the infant universe's structure. But in 2005, researchers studying data from NAS, a Wilkinson microwave anisotropy probe, stumbled onto something unsettling. Certain fluctuations in the CMB weren't random. They were aligned, mysteriously correlated with the plane of our solar system. Dubbed the axis of evil for the headaches it caused cosmologists, this oddity suggests either an unthinkable cosmic conspiracy or a flaw in our most cherished theories about the universe's origins. At first glance, the alignment seems laughably improbable. The solar system is an insignificant speck. Why would the universe's oldest light pattern itself around our tiny corner of space? One explanation is sheer coincidence, a statistical fluke in the noise. After all, if you flip a coin enough times, you'll eventually get 10 heads in a row. But the odds of this particular alignment happening by chance are less than 1 in 1,000. That's like shuffling a deck of cards and drawing the same royal flush 3 times straight. Possible, technically, likely, not remotely. Then there's observational bias. Could our measurements somehow be contaminated? Earth's motion through the cosmos creates a subtle Doppler shift in the CMB data, like the way a siren's pitch changes as an ambulance speeds past. Scientists correct for this, but what if hidden errors linger? Dust in our galaxy or quirks in telescope calibration might imprint false patterns. Yet after years of cross-checking with more sensitive instruments like the Planck satellite, the anomaly persists. It's not the data, it's the universe itself that seems off-kilter. This is where theories get radical. Some physicists suggest the axis of evil hints at a pre-Big Bang universe. Picture our cosmos as a bubble floating in a vast multiverse. If a previous universe collapsed and rebounded in the Big Bang, its structure might have left imprints on us like wrinkles in a reshaped sheet of space-time. The alignment could be a cosmic scar, a ghostly reminder of what came before. Others propose even wilder ideas, that the universe has a preferred direction, violating Einstein's assumption that space looks the same in all directions. It's as if we've spent centuries believing Earth is flat, only to stumble upon a compass that points somewhere else. But perhaps the most unsettling possibility is this. The axis of evil might be evidence that we're seeing the universe from a special place. Modern cosmology rests on the Copernican principle, the idea that Earth isn't central or unique. If the CMB truly revolves around our solar system's orientation, it upends that foundational belief. Suddenly, we're back in a pre-Copernican world where humanity's address seems suspiciously privileged. Whether it's a quirk of physics, a shadow of a larger reality, or just an error we haven't found yet, the axis of evil remains one of cosmology's greatest unresolved riddles. And that's the beauty of it. Sometimes the universe doesn't just hand us answers, it hands us paradoxes, daring us to look deeper. Mars has been playing a cosmic game of hide and seek with scientists for decades, and the prize is methane. This simple molecule, made of 1 carbon atom and 4 hydrogen atoms, shouldn't linger long in the red planet's thin atmosphere. Sunlight and chemical reactions should break it apart within a few hundred years. Yet since 2003, orbiters, landers, and telescopes have sporadically detected methane plumes, sometimes in bursts 10 times stronger than background levels, only to vanish weeks later. It's like catching a whiff of smoke in a forest, but when you turn to look, the fire's already gone. So where's it coming from? One tantalizing possibility is biology. On Earth, over 90% of methane is produced by living organisms, from burping cows to subterranean microbes. If similar life exists on Mars, perhaps clinging to existence in deep aquifers or soil pockets, it could be exhaling methane as a byproduct. The idea gains traction from Curiosity rover's findings. In 2019, it measured a methane spike 21 parts per billion, the highest ever recorded. Even more intriguing, these spikes often peak during Martian summer, when warmer temperatures might stimulate microbial activity. But before we declare life on Mars, let's talk geology. Methane can also arise from serpentinization, a chemical reaction between water, carbon dioxide, and certain minerals like olivine common in Mars's volcanic regions. Heat and pressure deep underground could be cooking methane like a slow geological oven, with cracks in the crust occasionally venting it to the surface. ESA's Trace Gas Orbiter even spotted methane near Cerberus Fossae, a network of tectonic fractures bolstering this theory. Then there's the comet hypothesis. Maybe ancient impacts delivered methane-rich ices that occasionally sublimate when disturbed. The real puzzle isn't just the methane source, it's the erratic disappearance. On Earth, methane sticks around for about a decade. Mars's vanishing acts suggest something's actively destroying it, and fast. Some suspect peroxides in Martian dust are oxidizing the methane, while others point to electric fields generated by dust devils which might zap the molecules apart. The wildest theory, ephemeral methane-munching microbes at the surface, creating a fleeting biosignature that self-erases. NASA's Perseverance rover is now hunting for answers with MOXIE, an instrument that could identify methane's carbon isotopes. Life tends to favor lighter isotopes, while geological processes don't discriminate. Until we crack this case, Mars's methane remains a tantalizing riddle, one that could rewrite our understanding of life's cosmic reach. Beyond Neptune's icy domain, something massive seems to be warping the paths of distant objects, an unseen hand sculpting their orbits into peculiar alignments. Astronomers first noticed the strange patterns in the early 2010s. A cluster of small icy bodies beyond Pluto were all swinging around the Sun at odd angles, their closest approaches oddly grouped in space. The odds of this happening randomly, less than 1 in 15,000. It's as if someone arranged the solar system's outer debris like hands on a clock, all pointing in the same general direction. The most exciting explanation, a hidden ninth planet 5 to 10 times Earth's mass, lurking 20 times farther out than Neptune. This hypothetical world, dubbed Planet 9, would follow a stretched, elliptical orbit so vast it could take up to 20,000 years to complete a single trip around the Sun. Its gravity would act like a cosmic shepherd, herding those wayward Kuiper Belt objects into their strange configurations. Computer simulations show the math works eerily well. Drop a Planet 9 into the outer solar system, and within a billion years, it perfectly replicates the orbital oddities we see today. But finding this ghostly world is like searching for a black marble in a pitch-black room using only a flickering candle. At such extreme distances, even a giant planet would reflect virtually no sunlight, perhaps shining at magnitude 22 or dimmer in our telescopes. Making matters worse, we only have rough guesses about its orbital path. It could be anywhere along a vast celestial highway spanning hundreds of years' worth of sky. Some researchers suggest alternative explanations. Could a rogue primordial black hole, no larger than a grapefruit but containing several Earth masses, be yanking on those distant orbits? It's a wild idea, but recent gravitational microlensing surveys have hinted at unseen compact objects drifting through our galaxy. Others propose a temporary imbalance caused by the collective gravity of countless smaller Kuiper Belt objects we haven't yet catalogued, like the murmuration of starlings creating shapes no single bird could predict. Yet Planet 9's fingerprints keep showing up. In 2021, astronomers discovered another batch of extreme trans-Neptunian objects with orbits tilted in lockstep, exactly as the hidden planet's influence would predict. Then came the peculiar case of a dwarf planet called Sedna, which loops out a staggering 940 astronomical units from the Sun with no obvious gravitational tether. Only something hefty nearby could have stranded it in such a lopsided orbit. The hunt continues with next-generation telescopes like the Vera Rubin Observatory, which will scan the entire southern sky with unprecedented sensitivity. If Planet 9 exists, it may soon step out of the shadows, or perhaps we'll uncover something even stranger, a cosmic prankster rewriting the rules of our solar system's backyard. Either way, the outer reaches have one thing in common with the best mystery novels. Just when you think you've cracked the case, the plot thickens. In the cosmic rulebook, dark matter isn't just a player, it's the invisible captain holding galaxies together with its gravitational grip. So when astronomers stumbled upon NGC 1052 DF2, a galaxy that appears to play by none of the usual rules, the discovery sent shockwaves through astrophysics. This ultra-diffuse galaxy, floating like a ghostly smudge in the constellation Cetus, has almost no dark matter at all. Its stars move sluggishly, their speeds betraying a gravitational pull that can be explained by visible matter alone. It's as if you removed the scaffolding from a skyscraper, only to find the building still standing, defying every blueprint we thought we knew. At first, skepticism ran high. Could this be a case of miscalibration, a cosmic mirage fooling our telescopes? After all, measuring dark matter isn't as simple as pointing a detector at the sky. Astronomers rely on indirect clues, like how fast stars orbit their galaxy's center. Faster spins mean more unseen mass, but DF2's stars crawl along, their motions matching the paltry pull of its visible stars and gas. Follow-up studies using the Keck Observatory and Hubble only cemented the anomaly. Even more baffling, DF2 isn't alone. Its neighbor, DF4, shows the same dark matter deficit, like a pair of cosmic rebels flouting the laws of physics. One explanation points to tidal stripping, the idea that a larger galaxy might have robbed DF2 of its dark matter long ago. Picture a galactic mugging, as DF2 drifted too close to a heavyweight like NGC 1052. Gravitational tides could have yanked away its dark matter while leaving the delicate stellar component intact. It's a plausible plot twist, but there's a catch. DF2 shows no signs of the violent distortions typical of such encounters. Its stars float undisturbed, like a ship sailing smoothly despite losing its anchor. Then there's the formation theory. Some models suggest DF2 could have been born differently, emerging from gas already stripped of dark matter. Imagine a cloud of pristine gas, never tainted by the invisible stuff, collapsing directly into stars. But this raises another question: how dark matter is thought to be the gravitational glue that enables gas to clump into galaxies in the first place. Without it, DF2's existence is like building a sandcastle without sand, a paradox that keeps theorists awake at night. The plot thickened in 2021 when a team claimed DF2 might actually be much closer than initially thought. Its apparent dark matter deficiency just a trick of perspective. But subsequent distance measurements, including those from Hubble, upheld the original findings. If anything, the debate highlights how much we still don't understand about these cosmic outliers. Could DF2 be a smoking gun for alternative gravity theories, like modified Newtonian dynamics? Proponents argue MOND could explain the galaxy's rotation without invoking dark matter at all. Yet even MOND struggles to account for DF2's extreme case, leaving critics to wonder if we're missing a piece of the puzzle, or if the puzzle itself needs rewriting. What makes DF2 so thrilling isn't just its defiance of expectations. It's a reminder that every time we think we've cracked the universe's code, nature throws us a curveball. Whether it's a galactic anomaly, a measurement error, or a sign of deeper physics waiting to be uncovered, one thing's clear: the cosmos still has a few tricks up its sleeve. And that's what makes exploring it so endlessly fascinating. Einstein's theory of general relativity paints gravity as the graceful curvature of spacetime, a cosmic stage where planets, stars, and galaxies perform their orbits. Meanwhile, quantum mechanics zooms in on the subatomic realm, where particles flicker in and out of existence, governed by probability and uncertainty. Both theories work brilliantly in their own domains, but when you try to merge them, the math explodes into nonsense. This is the quantum gravity conundrum, the glaring rift at the heart of modern physics, and solving it might require rewriting the rules of reality itself. Enter string theory, the most glamorous contender in the unification game. It proposes that all particles aren't dots but tiny, vibrating strings with different harmonies corresponding to different forces. Picture a cosmic symphony where gravity, electromagnetism, and the nuclear forces are just notes played on the same strings. The catch: these strings exist in 10 or 11 dimensions, far beyond our familiar 4, curled up so tightly we'll likely never detect them directly. Some versions even suggest our universe is a hologram, its true workings encoded on a distant, higher dimensional surface. It's a breathtaking vision, but after 50 years, string theory still lacks experimental proof, leaving critics to wonder if it's math or metaphysics. Then there's loop quantum gravity, string theory's scrappy underdog sibling. Instead of extra dimensions, it chops space-time itself into discrete, finite loops. Think of it as the universe's pixels. At the tiniest scales, space-time becomes a frothy network of interconnected nodes, smoothing out the infinite singularities that plague black holes and the Big Bang. In this view, the fabric of reality isn't continuous but stitched together like chainmail. While less flashy than string theory, loops offer testable predictions like subtle tweaks to the speed of light at extreme energies. The trouble: we'd need a particle accelerator the size of a galaxy to check. But what if gravity isn't fundamental at all? That's the radical premise of emergent gravity, championed by physicist Eric Verland. He argues gravity is a side effect of entropy, the universe's tendency toward disorder emerging from the way information is arranged in space-time, much like how temperature arises from atomic motion. It's like realizing the force pushing you back in a car isn't a force at all, just inertia. If true, dark matter might be an illusion, a mirage caused by our misunderstanding of gravity's true nature. Early calculations match galactic rotation curves eerily well, but the theory struggles to explain larger cosmic structures without tweaks. Here's the rub: each approach solves one piece of the puzzle while leaving others untouched. String theory unifies forces but floats untethered from experiment. Loop quantum gravity quantizes space but stumbles on unifying other forces. Emergent gravity ditches dark matter but can't yet explain the Big Bang. And lurking behind it all is the unsettling possibility that we're grasping at shadows, missing something fundamental like Newton before Einstein or Einstein before quantum mechanics. Perhaps the answer lies in the gaps between these theories or in something entirely unforeseen. After all, the history of physics is littered with ideas too strange to be believed until they weren't. Until then, the quantum gravity conundrum stands as both a monument to human curiosity and a humbling reminder: the universe owes us nothing, especially not simplicity. Deep in the void between galaxies, cosmic rays, subatomic particles accelerated to nearly light speed, zip through the universe. Most come from familiar sources: exploding stars, solar flares, even our own Milky Way's magnetic fields. But a rare few defy explanation. These ultra-high-energy cosmic rays carry as much punch as a major league fastball packed into a single particle. They're so powerful, in fact, that physics says they shouldn't exist. Their energy exceeds what any known cosmic accelerator, even the most violent black holes, should be capable of producing. Yet here they are, raining down on Earth in a mystery that's puzzled scientists for decades. The first clue came in 1962 when detectors in New Mexico recorded a cosmic ray with the energy of a falling brick, all concentrated in a single proton. Dubbed the "oh my god" particle, it shouldn't have been able to travel far without losing energy to collisions with the cosmic microwave background, yet somehow it reached us. Since then, observatories like the Pierre Auger Array in Argentina have spotted dozens more of these extreme outliers, each arriving from random directions with no obvious source. It's like finding bullets shot at you from a gun that doesn't appear to exist. One leading suspect: active galactic nuclei, the supermassive black holes at the hearts of galaxies. As these monsters devour matter, they spew jets of plasma powerful enough to accelerate particles to extreme energies. But here's the snag: these rays arrive isotropically, scattered evenly across the sky. If they came from nearby Aegean, we'd expect them to cluster in the direction of known sources. Unless, of course, something's bending their paths en route like intergalactic magnetic fields strong enough to curve their trajectories beyond recognition. Then there's the exotic particle theory. Could these rays be Strangelets' hypothetical nuggets of strange matter made of up, down, and strange quarks? Unlike normal matter, Strangelets might be ultra-dense and stable, capable of surviving interstellar journeys intact. If one slammed into Earth's atmosphere, it could unleash a cascade of particles mimicking an ultra-high-energy cosmic ray. It's a long shot, but not impossible, especially if Strangelets formed in the quark-gluon plasma of the early universe and have been drifting ever since. The wildest idea, these particles might be relics of cosmic strings defects in space-time left over from the Big Bang. Picture the universe cooling like molten glass, forming cracks that vibrate with unimaginable energy. If two strings snapped together, they could release enough power to launch particles beyond anything we've ever seen. It's speculative, yes, but when conventional physics falls short, sometimes you need to think outside the galaxy. What makes this mystery so thrilling isn't just the particles themselves, it's what they reveal about the universe's extremes. Every time one of these cosmic speedsters streaks through our detectors, it's a reminder. The cosmos still holds accelerators beyond our wildest theories, and the rules we thought were set in stone might just be pencil sketches waiting to be erased. In the vast tapestry of cosmic oddities, few objects are as geometrically striking as the Red Rectangle Nebula. Named for its sharp, angular appearance and crimson glow, this nebula lies about 2,300 light-years away in the constellation Monoceros. At first glance, it looks less like a celestial object and more like a piece of abstract art, a glowing red X framed by a rectangular haze, defying the usual billowy, asymmetrical shapes of most nebulae. The precision of its structure is so uncanny, it's as if the universe grabbed a ruler and protractor to sketch it into existence. What could explain this cosmic symmetry? The leading theory points to HD 44179, the binary star system at the nebula's heart. These two stars, a dying red giant and a smaller, hotter companion, orbit each other in a tight dance, spinning off layers of gas and dust in precise, opposing jets. Think of a spinning lawn sprinkler, but instead of water, it's flinging star stuff into space in perfectly mirrored outflows. Over time, these ejections sculpted the nebula's distinctive X shape, with the rectangular halo forming from light reflecting off dust particles in the surrounding disk. But here's the twist: binary stars aren't rare, yet we don't see other nebulae with this level of geometric perfection. That's where the light echo hypothesis comes in. Some researchers suggest the red rectangle's sharp edges might be an illusion, a trick of perspective where light from the central stars bounces off dust layers in a way that amplifies its angular appearance. Picture shining a flashlight into a foggy room. If the fog is layered just right, the beam might cast startlingly sharp shadows. If this is the case, the nebula's structure could be more ephemeral than it seems, a fleeting alignment that will dissolve as the dust disperses. Then there's the mystery of its vibrant red hue. Most planetary nebulae glow in blues and greens from ionized oxygen and nitrogen, but the red rectangle's crimson comes from a rare form of carbon-rich molecules called polycyclic aromatic hydrocarbons, or PAH. These complex organic compounds thrive in the nebula's dense dust lanes, fluorescing under the star's ultraviolet light like cosmic neon signs. Intriguingly, PAHs are also found in meteorites and interstellar space, raising tantalizing questions about their role in seeding the building blocks of life. Could nebulae like this be cosmic factories for organic chemistry? The red rectangle's defiance of typical nebula models makes it a laboratory for testing astrophysical extremes. Its precise shape challenges our understanding of how stellar winds interact, how dust aligns in space, and even how binary stars choreograph their final act. And with the central red giant nearing the end of its life, we're witnessing a fleeting masterpiece, a cosmic structure that, in a few thousand years, will fade into the darkness, leaving behind only a white dwarf and a trail of unanswered questions. For now, it stands as a reminder that even in the chaos of the universe, there's room for geometry so perfect it feels almost intentional. If you took every atom in every star, planet, and speck of dust we can see in the universe and weighed them, you'd only account for about half of the ordinary matter that should exist. That's the essence of the missing baryon problem, a cosmic accounting error where roughly 50% of the universe's expected normal matter seems to have vanished without a trace. Baryons, the particles that make up atoms, are the building blocks of everything tangible from your body to distant galaxies. Yet when cosmologists tally up what's observable, stars, gas clouds, interstellar dust, the numbers fall shockingly short of predictions based on the Big Bang's afterglow and the universe's large-scale structure. It's like meticulously counting every grain of sand on a beach, only to realize half the sand you expected is mysteriously absent. So where could this missing matter be hiding? The leading suspect isn't some exotic, unseen dimension. It's far more mundane and yet fiendishly difficult to detect. Vast, diffuse webs of superheated gas strung between galaxies like cosmic spider silk. Known as the warm-hot intergalactic medium, or WIM, these filaments are theorized to contain temperatures between 100,000 and 10 million degrees too hot to form stars or emit visible light, but too cool to glow brightly in X-rays. Imagine trying to spot a thin veil of steam in a pitch-black room using only a flashlight. That's the challenge astronomers face when hunting for WIM. The first breakthrough came in 2018 when researchers used the shadowy fingerprints of distant quasars to probe these elusive structures. As light from quasars' extremely bright galactic cores travels through the cosmos, it passes through WIM filaments which absorb specific wavelengths of ultraviolet light. By stacking data from thousands of quasar observations, scientists found the telltale absorption lines of highly ionized oxygen, carbon, and neon, the chemical breadcrumbs of WIM's scorching gas. These findings suggested that WIM could account for up to 40% of the missing baryons, woven into the cosmic web's invisible threads, but the search didn't stop there. Another potential reservoir lies in the halos of galaxies, where clouds of million-degree gas swirl in extended, faint cocoons. The Chandra X-ray Observatory detected traces of this gas around the Milky Way and nearby galaxies, but its density is so low that mapping it comprehensively remains a monumental task. Even more elusive are the circumgalactic mediums, enormous, faint clouds of gas orbiting galaxies like ghostly atmospheres. Simulations suggest these could hoard another significant fraction of the missing matter, but their faint emissions blur into the background noise of the universe. Then there's the intergalactic transfer theory. When galaxies collide, violent gravitational interactions can eject torrents of baryonic matter into deep space, flinging it far beyond where telescopes typically search. These lost atoms might linger in intergalactic voids, drifting like cosmic runoff. Supporting this idea, the Hubble Space Telescope found evidence of scattered, ionized hydrogen in the voids between galaxy clusters, gas so thin it's nearly transparent, but collectively massive enough to tip the scales. The missing baryon problem isn't just about balancing a cosmic ledger. It's a fundamental test of whether we understand how matter organizes itself across the universe's grandest scales. Every new detection method, whether stacking quasar spectra, hunting for faint X-ray emissions, or mapping plasma with radio telescopes, brings us closer to solving the puzzle. And with upcoming observatories like the Athena X-ray telescope and the Square Kilometre Array poised to peer deeper into these shadowy reservoirs, we might soon close the gap between prediction and observation. Until then, the universe's hidden baryons serve as a humbling reminder. Sometimes what's invisible holds the key to what's real. High above Earth, hidden in the orbital graveyard of defunct satellites and space junk, lurks a legend wrapped in static and speculation, the Black Knight satellite. Stories claim this mysterious object has been orbiting our planet for 13,000 years, an ancient alien probe silently watching humanity's ascent. The myth took flight in 1954 when newspapers reported that the U.S. Air Force had detected two unexplained satellites circling Earth years before Sputnik became humanity's first artificial moon. Conspiracy theorists seized on the tale, weaving it into a tapestry of extraterrestrial surveillance, with some even attributing the artifact to Nikola Tesla, who claimed in 1899 to have intercepted odd radio signals that might have originated from it. But what's really up there, the truth is far less cinematic, though no less fascinating. Modern astronomers trace the Black Knight's origins to a 1998 Space Shuttle Endeavour mission, where astronauts photographed a rogue thermal blanket lost during an earlier spacewalk. The silvery debris, tumbling end over end in sunlight, bore an uncanny resemblance to the sleek, geometric shapes described in UFO lore. As for those eerie radio signals, they're likely pulsars, distant, rotating neutron stars emitting regular pulses of radiation, or earthly interference misread as extraterrestrial chatter. Yet the myth endures, fueled in part by grainy images of unidentified orbital objects and the natural human tendency to see patterns in randomness. Space is cluttered with defunct satellites, spent rocket stages, and fragments from collisions. Over 26,000 trackable pieces of debris whiz around Earth at 17,000 miles per hour. Against this chaotic backdrop, it's easy to mistake a drifting panel or stray bolt for something more sinister. Even the International Space Station occasionally spots unidentified objects that turn out to be mundane fragments upon closer inspection. Why does the Black Knight legend persist? It taps into deep-rooted narratives about lost civilizations and hidden knowledge, the idea that advanced beings once visited Earth, leaving behind clues we're only now rediscovering. The vacuum of space, with its impenetrable darkness and unanswered questions, becomes a canvas for our imagination. And in an era where governments declassify UFO footage and billionaires hunt for alien megastructures, the line between science and speculation feels blurrier than ever. The Black Knight's legacy isn't just about space debris or mistaken identity. It's a mirror reflecting our longing for connection in a vast, seemingly indifferent universe. Every unexplained blip on a radar screen, every anomalous orbit, becomes a Rorschach test. Do we see cold, hard physics or something more? Until a smoking gun emerges, the myth will likely keep orbiting right alongside the truth, two sides of humanity's eternal cosmic curiosity. Deep in the constellation Boötes lies a cosmic anomaly so vast it defies imagination, the Boötes Void, a spherical region of space spanning 330 million light-years where galaxies are nearly absent. To put that in perspective, if the Milky Way were a grain of sand, this void would be the size of a football stadium. Most cosmic voids are gaps in the web-like structure of the universe, but the Boötes Void is different. It's not just empty, it's stunningly empty, with only 60 galaxies found where thousands should exist. It's as if someone took a cosmic eraser and scrubbed out a chunk of the universe. One explanation points to the quirks of the early universe. During the Big Bang, quantum fluctuations seeded tiny density variations that grew into galaxies and clusters. But what if, in rare pockets, those fluctuations were so minimal that matter never clumped together? The Boötes Void could be one such statistical fluke, a place where the cosmic dice rolled snake eyes, leaving an immense barren bubble. If true, it's a fossil from the universe's infancy, a frozen snapshot of primordial nothingness. But here's where things get speculative. Could advanced civilizations have played a role? The idea sounds like sci-fi, but the Kardashev scale, a framework for ranking hypothetical advanced societies, suggests a Type 3 civilization might harness energy on a galactic scale. If such beings existed long ago, they might have rearranged or consumed entire galaxies, leaving behind a sterile void. It's a fringe theory, to be sure, but it raises a chilling question. Could the Boötes void be evidence of a civilization so advanced it rendered itself invisible? More plausibly, the void might be the result of multiple smaller voids merging over eons. Imagine soap bubbles combining into one colossal pocket. Gravity could have drawn galaxies outward, leaving an ever-expanding desert in the center. Supporting this, some simulations show how galactic superclusters might act like cosmic vacuum cleaners, pulling matter away from certain regions over billions of years. Yet even these explanations struggle to account for the void's sheer scale and emptiness. Some theorists propose a darker twist. What if the void isn't empty at all, but filled with something we can't see? Dark energy, which drives the universe's accelerating expansion, might operate unevenly, creating vast dead zones where matter is pushed apart more aggressively. Or perhaps the void contains a concentrated knot of dark matter so dense it repels normal matter, like a gravitational magnet with the wrong polarity. The Boötes void challenges our understanding of cosmic structure and forces us to rethink how emptiness fits into the grand tapestry of the universe. It's a reminder that space isn't just about what's there, it's also about what isn't, and in that absence we find some of the most profound mysteries of all. Black holes famously drag everything in, shredding stars and swallowing light itself. But what if the universe has an escape hatch? Enter white holes, the hypothetical twins of black holes where nothing can enter, only exit. If black holes are cosmic one-way streets, white holes would be their unruly counterparts, spewing out matter and energy with unstoppable force. The math of general relativity allows for such objects, but the catch is this: we've never seen one. They exist as tantalizing possibilities in equations, cosmic mirages flickering at the edges of theoretical physics. Take the idea of a black hole's singularity, a point of infinite density where spacetime curvature goes haywire. Some models suggest that beyond this point, the singularity might bounce, transforming into a white hole. Picture a collapsed star not ending in crushing oblivion, but rebounding like a rubber band stretched to its limit, firing its contents back into the universe. It's a cosmic redemption arc. What goes into a black hole might not be lost forever, just delayed. But why haven't we spotted these cosmic geysers? For starters, a white hole would be spectacularly unstable. Unlike black holes, which form from collapsing stars and persist for eons, white holes would theoretically erupt in a violent burst of energy, then vanish. If one existed in our cosmic neighborhood, we'd expect fireworks, gamma-ray bursts, or jets of particles blazing across the sky. Yet the sky remains suspiciously quiet. Some theorists argue that white holes could have been more common in the early universe, their eruptions mistaken for primordial Big Bang echoes. Others speculate they might hide in plain sight, masquerading as mysterious fast radio bursts or even the elusive dark matter. Then there's the wild card, wormholes. If Einstein-Rosen bridges hypothetical tunnels through space-time are real, white holes could be the exit doors. Imagine a black hole in one corner of the universe connected to a white hole in another, a secret subway system for matter. The problem: wormholes demand exotic matter with negative energy to stay open, a substance we've never found. Without it, these tunnels would snap shut faster than a cosmic mousetrap. Perhaps the most haunting question is this: if white holes exist, where's all the stuff they're supposedly spitting out? Black holes have feasted on galaxies for billions of years. If even a fraction of that matter re-emerged via white holes, the cosmos should be littered with their fingerprints. Instead, we're left with equations that whisper of their possibility and a universe that stays stubbornly silent. That silence might be the clue. Some physicists propose white holes aren't standalone objects but fleeting moments in black hole evolution, a final gasp before fading into nothing. Or maybe they're locked away in other dimensions, their eruptions invisible to our telescopes. For now, white holes remain ghosts in the machine of relativity, reminding us that the universe's rules might be stranger than we dare imagine. And if they're out there, hiding in the math, they could rewrite not just the fate of black holes, but the story of existence itself. Look up at the night sky just before dawn or after dusk, and you might catch a faint, ghostly glow stretching upward from the horizon, a pyramid of soft light following the same path the sun takes by day. This eerie radiance, known as the zodiacal light, has puzzled sky watchers for centuries. Traditionally, astronomers pin the glow on interplanetary dust, tiny particles scattered along the plane of our solar system, reflecting sunlight like a cosmic highway of glitter. But recent discoveries suggest this dusty explanation might be incomplete, hinting at hidden celestial objects or even stranger possibilities lurking in the inner solar system. For decades, the textbook story went like this. As comets streak sunward, their ices vaporize, leaving behind trails of dust. Asteroids, too, grind against each other over eons, filling space with microscopic debris. This dust settles into a vast, lens-shaped cloud centered on the sun, concentrated along the ecliptic, the same plane where planets orbit. When sunlight hits these particles, they scatter its rays, creating the zodiacal glow. It's a tidy theory supported by spacecraft like NASA's Juno probe, which detected dust grains during its journey to Jupiter. But here's the catch: some observations don't fit. The zodiacal light is brighter and more structured than simple dust should produce. Infrared surveys reveal puzzling clumps and asymmetries in the dust cloud features that suggest something more dynamic at play. One provocative idea points to undiscovered asteroid populations, swarms of rocks hidden in the inner solar system, too faint to spot but numerous enough to contribute extra debris. In 2020, astronomers discovered the first of these co-orbital asteroids, dubbed 2020 AV2, looping around the Sun entirely within Venus's orbit. Could there be more, shedding dust as they collide or crumble? Then there's the wild card: exotic particles. Some theorists propose that a fraction of the zodiacal light might come from dark matter annihilations or hypothetical particles called actions, which could convert to photons in the Sun's magnetic field. It's a long shot, but if true, it would mean our solar system's ethereal glow isn't just dust, it's a window into fundamental physics. The zodiacal light might seem like a minor curiosity, but solving its riddles could reshape our understanding of the solar system's hidden architecture. Whether it's unseen asteroids, new physics, or just dust behaving in ways we don't yet grasp, this celestial whisper reminds us that even the most familiar skies hold secrets waiting to be decoded. The universe is expanding, that much we know, but the exact rate of that expansion has become one of the most heated debates in modern cosmology. Meet the Hubble tension, a stubborn discrepancy that's splitting astrophysics into camps. On one side, we have measurements based on the cosmic microwave background, the afterglow of the Big Bang suggesting the universe expands at about 67 kilometers per second per megaparsec. On the other, observations of nearby supernovas and Cepheid stars peg the number closer to 73. That gap might seem small, but in the precise world of cosmology, it's a chasm. Either we're missing something fundamental about how the universe works, or our tools are lying to us in ways we don't yet understand. Let's break down the contenders. The cosmic microwave background, mapped by missions like Planck, acts as a baby picture of the universe, frozen in time just 380,000 years after the Big Bang. From those primordial ripples, scientists extrapolate the expansion rate using our best models of dark matter and dark energy. But here's the catch: those models assume these mysterious forces have behaved consistently over time. What if they haven't? Some theorists propose dark energy, the force accelerating cosmic expansion, might be evolving, growing stronger or weirder as the universe ages. Imagine blowing up a balloon that suddenly starts inflating faster for no apparent reason. That's the kind of curveball dark energy could be throwing. Then there's the Local Universe Camp, led by the Hubble Space Telescope's meticulous observations of pulsating Cepheid stars and Type Ia supernovas. These cosmic yardsticks let astronomers measure distances and velocities directly, building a modern distance ladder to calculate the expansion rate. Their higher value 73 has held firm across multiple studies, even as methods improve. Skeptics argue hidden errors might lurk in the calibration of these measurements, like misjudging the brightness of certain stars or the dust obscuring them. But after years of cross-checking, the discrepancy won't vanish. It's as if the universe's early and late chapters were written in slightly different dialects. Now the plot thickens. Enter Baryons acoustic oscillations, the faint, fossilized sound waves from the early universe imprinted in galaxy distributions. These should bridge the gap, but their results awkwardly straddle the two values, deepening the mystery. Meanwhile, alternative theories are bubbling up. Could undiscovered particles be tweaking gravity on cosmic scales? Or might the universe be lumpier than we thought, with dense regions tugging on measurements like invisible magnets? Some even float the idea of a dark radiation component, an extra dose of energy in the early cosmos that skewed its expansion fingerprint, the stakes. If the tension points to new physics, it could upend our understanding of dark energy, gravity, or even the Big Bang itself. If it's systematic error, it means our gold standard tools need recalibrating, a humbling but crucial fix. Either way, the Hubble tension isn't just a technical hiccup. It's a cosmic crossroads forcing us to ask, are we missing a piece of the puzzle, or is the puzzle itself far stranger than we ever imagined? Imagine tuning a cosmic radio and suddenly catching a blip, a burst of energy so intense it outshines entire galaxies, but lasting only milliseconds. These are fast radio bursts, or FRB, some of the most enigmatic signals in the universe. First discovered in 2007, these flashes originate far beyond our galaxy, packing as much energy as the sun emits in days into a flicker shorter than the blink of an eye. What could possibly produce such extreme, fleeting signals? The theories are as wild as the bursts themselves, spanning the realms of known physics and venturing into the speculative. One prime suspect, magnetars, the universe's ultimate cosmic tantrum throwers. These neutron stars, collapsed stellar cores with magnetic fields 1 trillion times stronger than Earth's, are prone to violent starquakes and magnetic eruptions. In 2020, astronomers got their best evidence yet when a magnetar in our own galaxy fired off an FRB-like blast. The catch: most FRBs come from billions of light years away, implying sources far more powerful than local magnetars. Could hyperactive magnetars in distant galaxies, or even more exotic objects like colliding neutron stars, be the culprits? The jury's still out, but magnetars remain leading contenders. Then there's the repeating FRB mystery. While most bursts are one-offs, a handful, like the famous FRB 1211, spit out signals over and over, sometimes in predictable patterns. This rules out cataclysmic one-time events like collisions or explosions, pointing instead to persistent engines capable of multiple eruptions. One provocative idea involves blitzars, neutron stars so massive they should collapse into black holes, but their rapid spin delays the inevitable. As they teeter on the edge, these dying stars might emit periodic death screams in the form of FRBs. Others speculate about highly magnetized asteroids plunging into neutron stars, triggering bursts each time they scrape the surface. But let's address the elephant in the cosmos. Could some FRBs be artificial? The narrowband nature of certain bursts concentrated at specific frequencies has drawn comparisons to engineered signals. Even the burst's luminosity fits theoretical models of interstellar beacons. Should an advanced civilization build planet-sized transmitters? While Occam's razor favors natural explanations, the possibility isn't entirely dismissed. After all, before pulsars were discovered, their precise radio pulses were briefly and seriously considered as potential alien broadcasts. Here's what makes FRBs so thrilling: they're more than just cosmic fireworks. By the time these signals reach us, they've traversed intergalactic space, subtly distorted by the plasma they've passed through. Like fingerprints, each burst carries imprints of the material between galaxies, material that's nearly invisible otherwise. FRBs could be the keys to mapping the universe's missing matter, the very glue holding galaxies together. And with new telescopes like the Canadian CHIME array spotting dozens of bursts monthly, we're on the verge of cracking their code. Whether they're magnetar tantrums, dying stars, or something even stranger, one thing's clear: the universe is broadcasting. We just need to learn how to listen. In the swirling acidic clouds of Venus, where temperatures roast metal and pressures crush submarines, scientists stumbled upon a molecule that shouldn't be there: phosphine. In September 2020, a team led by astronomer Jane Greaves announced they detected this stinky, flammable gas in Venus's upper atmosphere using the James Clerk Maxwell Telescope in Hawaii, and later confirmed it with the ALMA array in Chile. On Earth, phosphine is either manufactured industrially or produced by microbes thriving in oxygen-free environments like swamps and animal guts. Finding it on Venus was like spotting a lit match in a thunderstorm, spectacularly out of place and begging for an explanation. Could this be our first whiff of extraterrestrial life? The initial excitement was electric. Venus's cloud deck, hovering 30 to 40 miles above its scorching surface, has long been eyed as a potential haven for extremophile microbes. At that altitude, temperatures and pressures are eerily Earth-like, and some theorists have imagined hardy bacteria floating in droplets of sulfuric acid, surviving on trace chemicals. Phosphine's presence seemed to fit this speculative puzzle, a possible metabolic byproduct wafting through the haze. But almost immediately, other researchers began punching holes in the claim. One critique centered on the data itself. The ALMA observations might have been skewed by calibration errors or interference from Earth's atmosphere. When the team reanalyzed the data with corrected settings, the phosphine signal shrank dramatically from 20 parts per billion to just 1. Then came the abiotic counterarguments. Venus's hellish surface is a geochemical factory, constantly churning out surprises. Could volcanoes be the culprits? While Venusian volcanoes don't spew phosphine directly, deep magma interactions with phosphorus-rich crustal rocks might produce it under extreme conditions. The problem: we've never observed this process anywhere in the solar system. Another idea involves sunlight reacting with sulfur dioxide and trace minerals in the clouds, though lab experiments show this pathway generates negligible phosphine at best. The most dramatic twist arrived in 2021 when a study proposed that the original detection wasn't phosphine at all, but ordinary sulfur dioxide, a gas we know exists in Venus's atmosphere. At certain wavelengths, sulfur dioxide can masquerade as phosphine in telescope data, creating a false positive. The debate grew so heated that by 2022, NASA and ESA fast-tracked new Venus missions to settle the matter. What makes this controversy so compelling isn't just the science, it's the philosophical tension between skepticism and wonder. The universe has fooled us before with false biosignatures, like the Mars meteorite fossils of 1996. Yet Venus keeps dangling clues, from mysterious ultraviolet absorbers in its clouds to episodic gas spikes we still can't explain. Whether phosphine turns out to be a fingerprint of life, a geochemical fluke, or an illusion in the data, this episode underscores a thrilling truth. Even our closest planetary neighbor still guards secrets that defy easy answers. And sometimes the most profound discoveries begin with a single, baffling molecule. Imagine two coins flipped on opposite sides of the universe, yet every time one lands heads, the other always lands tails instantaneously, no matter how far apart they are. This isn't science fiction, it's quantum entanglement, a phenomenon so bizarre Einstein famously called it spooky action at a distance. Today, we're not just proving this spookiness is real, we're using it to test the very fabric of space-time itself. The magic starts with particles like photons or electrons becoming entangled, their properties linked in a way that measuring one instantly defines the other, even if separated by light years. In 2017, Chinese scientists shattered records by entangling photons between Earth and a satellite called Micius, separated by 1,200 kilometers. The results a perfect correlation, faster than light could have carried the information. It's as if the universe maintains a hidden hotline between particles, bypassing the cosmic speed limit we thought was unbreakable. This raises a jaw-dropping question. Does entanglement violate causality, the law that effects must follow causes? Not quite. While the outcome of measuring one particle seems to influence its twin instantly, no actual information is transmitted. You can't use entanglement to send a message faster than light. It's more like opening a locked box on Earth to find a blue marble, and knowing without looking that a box on Mars instantly holds a red one. The colors were always linked, you just didn't know which was which until you peeked, but here's where it gets cosmic. Some theorists propose entanglement might stitch space-time itself together. Think of the universe as a vast network of entangled particles, their connections forming the substrate of reality, like invisible threads weaving the cosmic tapestry. This idea, called entanglement equals wormholes, suggests that deeply entangled particles could be linked by microscopic bridges through space-time, akin to Einstein-Rosen bridges. It's a radical vision where quantum weirdness and relativity aren't enemies but two sides of the same coin. Meanwhile, labs are pushing further. Quantum satellites now aim to entangle particles across intercontinental distances, while underground experiments hunt for entanglement between Earth and passing cosmic rays. Some even dream of entangling macroscopic objects, tiny diamonds or mirrors, to see if the spookiness scales up. If it does, we might unlock technologies like ultra-secure quantum networks or sensors that detect gravitational waves by measuring their subtle tug on entangled atoms. Yet the grandest implication lingers in the realm of theory. If entanglement truly underpins space-time, it could rewrite our origin story. The Big Bang might have been a quantum phase transition, with all particles born entangled in a primordial fireball. Today's universe, with its apparent separations, could just be an illusion, a cosmic magic trick where everything is still subtly connected in ways we're only beginning to glimpse. One thing's certain, entanglement isn't just a lab curiosity anymore. It's a flashlight shining into the universe's deepest shadows, revealing a reality far stranger and far more interconnected than Einstein ever imagined. In a universe teeming with stars, one idea has captivated both scientists and science fiction fans alike. What if advanced civilizations aren't just out there, but they've built structures so colossal they eclipse entire suns? Enter the Dyson Sphere, a hypothetical megastructure first proposed by physicist Freeman Dyson in 1960. The concept is staggeringly simple yet mind-bending in scale. A civilization harnessing all the energy of its host star by surrounding it with a swarm of orbiting panels or even a solid shell capturing every last photon. The result, a star that shines unnaturally dim in visible light but glows fiercely in infrared, radiating waste heat from the energy harvesting operation. Astronomers have been hunting for these cosmic power plants for decades, scouring the skies for stars that defy natural expectations. The method relies on a simple principle: energy can't vanish. If a civilization redirects a star's light for its own use, the radiation must emerge as heat eventually. That means a Dyson Sphere candidate wouldn't just be dim. It would scream its presence in the infrared spectrum like a light bulb wrapped in a blanket, cool to the eye but warm to the touch. Telescopes like NASA WISE and Spitzer have scanned millions of stars for this telltale imbalance, flagging bizarre objects like KIC 8462852, better known as Tabby's star, which dims erratically in ways we still can't fully explain. Yet the hunt is tangled with false alarms and cosmic red herrings. Natural phenomena like thick dust clouds or young stars still shrouded in planetary debris and mimic Dyson Sphere's infrared excess. Take the case of the red and dead stars observed by the Infrared Astronomical Satellite in the 1980s. These stars showed extreme infrared emissions, sparking excitement, until follow-up studies revealed they were just ancient suns cloaked in self-generated dust, their own death throes masquerading as alien engineering. The challenges don't end there. Even if we spot a perfect candidate, how could we distinguish a megastructure from something equally exotic but natural? Some theorists propose looking for unnatural patterns like a star whose light flickers in geometric rather than random ways, or one whose infrared signature shifts abruptly as if panels were being adjusted. Others suggest searching for Dyson swarms, vast constellations of individual energy collectors orbiting a star in synchronized formations, their combined shadows creating a telltale twinkle in the star's brightness. But here's the twist: the absence of definitive proof might itself be a clue. Advanced civilizations could be using technologies beyond our current imagination, perhaps harvesting energy in ways that leave no thermal trace or tapping into dark energy directly. Or maybe they're deliberately hiding a concept known as the zoo hypothesis, where advanced beings avoid contact to let humanity develop undisturbed. The Dyson Sphere hunt isn't just about finding aliens, it's a testbed for our own ingenuity. Projects like the Breakthrough Listen initiative are refining ways to scan for not just infrared anomalies, but also laser pulses or artificial radio signals. Meanwhile, next-gen telescopes like the James Webb Space Telescope could uncover even subtler discrepancies in starlight, peeling back layers of cosmic mystery. Whether we ever find a Dyson Sphere or not, the search reshapes how we think about intelligence, energy, and survival in an ever-expanding universe. It forces us to ask, if we had the technology, would we build one? And if so, what might be watching us from the shadows, wondering the same thing? What if everything around us, the stars, the laws of physics, even your own thoughts, weren't real, but lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a theory that's leaped from sci-fi trope to serious scientific debate. At its core is a startling proposition. Our universe might not be the base layer of reality, but an artificial construct, like an ultra-realistic video game run by some higher dimensional civilization. And while it sounds like something straight out of the Matrix, some of the smartest minds in physics and philosophy aren't laughing it off. One of the earliest formal arguments came from philosopher Nick Bostrom in 2003. He laid out a trilemma. Either advanced civilizations always go extinct before developing simulation technology, they choose not to simulate universes, or we're almost certainly living in one. The logic hinges on statistics. If even one civilization ever reaches the capability to create ancestor simulations with conscious beings inside, the number of simulated minds would vastly outnumber organic ones. Put bluntly, the odds favor us being someone else's digital project. But where's the evidence? Proponents point to cosmic quirks that feel suspiciously like glitches or optimizations. Take the speed of light, a universal speed limit that seems arbitrarily set to prevent infinite energy or causality violations, much like a game engine capping frame rates to avoid crashes. Or consider quantum mechanics, where particles exist in fuzzy superpositions until observed, as if the simulation conserves processing power by only rendering reality when necessary. Even mathematical constants like pi or the fine structure constant appear fine-tuned to allow for complexity, almost like preset parameters in a coding environment. Not everyone's convinced. Critics argue these glitches are just gaps in our current understanding, not proof of a digital overlay. After all, the universe is under no obligation to make intuitive sense to human brains. And then there's the problem of infinite regression. If we're in a simulation, who's to say our simulators aren't also simulated ad infinitum? Some physicists, like Sabine Hossenfelder, dismiss the hypothesis as untestable, a modern-day philosophical zombie that borrows the language of science without offering falsifiable predictions. Yet the idea keeps evolving. In 2016, billionaire Elon Musk famously declared the odds we're not in a simulation are 1 in billions. Around the same time, physicists like Silas Bean explored potential signatures of simulated universes, like tiny anomalies in high-energy particle behavior or geometric patterns hidden in cosmic rays, artifacts of a finite computational grid. Others suggest looking for compression artifacts in the fabric of reality, like rounding errors in the values of fundamental constants at extreme decimal places. The simulation hypothesis forces us to confront existential questions that blur science and philosophy. If this is a simulation, does free will exist, or are we following deterministic scripts? Would discovering our artificial nature unravel the meaning of existence, or would it simply be another Copernican revolution, dethroning humanity from the center of reality once again? Maybe the most haunting question isn't whether we're in a simulation, but why we were built and if the simulators are still watching. Whether you find the idea exhilarating or unsettling, one thing's clear: the universe is strange enough that even the wildest theories can't be ruled out. And that's what makes this hypothesis so compelling, not because it's proven, but because it challenges us to ask what a real even means in a cosmos where reality might have layers we've only begun to imagine. From dark matter's invisible grip to the eerie silence of the Fermi paradox, from black holes leaking information to the cosmic mirage of the Great Attractor, we've journeyed through 30 of the most astonishing theories that attempt to crack the universe's biggest mysteries. And yet, here's the humbling truth: for every answer we think we've found, a dozen new questions erupt. The cosmos isn't just a puzzle with missing pieces, it's a puzzle where the pieces keep changing shape. Think about it: we've mapped the afterglow of the Big Bang, but we still don't know what triggered it. We've detected gravitational waves from colliding black holes, yet we can't explain why 95% of the universe is made of stuff we can't see or touch. Even our best guesses, like string theory or the holographic principle, feel like waving a flashlight in a cavernous void, illuminating only fragments of the truth. What makes these theories so exhilarating isn't just their audacity, it's the reminder that the universe refuses to be boxed in. The same scientists who proposed Dyson spheres and simulated realities will be the first to admit we might be dead wrong. And that's the beauty of it. Every anomalous signal, every orbital oddity, every flicker of light that defies explanation is an invitation to question, to imagine, to push beyond the edges of our understanding. So now it's your turn. Which of these theories left you staring at the ceiling at 3 a.m., your brain buzzing with possibilities? Was it the spine-tingling idea that we might live in a hologram? The haunting possibility that dark energy could one day rip space-time apart? Or the notion that Oumuamua wasn't just a space rock, but a relic of some distant civilization? Drop your favorite in the comments. I'd love to hear which cosmic head-scratcher hooked you hardest. And if you're hungry for more mysteries, from rogue planets to time-bending singularities, hit that subscribe button. The universe is stranger than we can suppose, and together we'll keep peeling back its layers, one mind-bending revelation at a time. After all, the greatest stories aren't the ones we've solved, they're the ones that keep us wondering.